Hi, my name is Langleite, and I am one of the master students at the Water Power Laboratory at NTNU. And this is my presentation about my master's thesis that has the title Test of a Francis turbine with variable speed operation. So, why variable speed operation? As we are trying to reduce our CO2 emission, this means that we have to produce more energy from renewable sources like solar, wind, and hydropower. And as you may know, solar and wind power is what we call intermittent energy. It is dependent on weather conditions, it has no storage capacity, and it is quite non-flexible. And when this type of energy is entering the grid, this could lead to challenges for the grid to keep its frequency stable. And that's why we have this flexible hydropower that have the capability to keep the frequency stable to a certain extent. But as this intermittent energy is increasing, this could forces the turbine to be operated at off design more often. And when runners are operated at off design, this could lead to fatigue and cracks due to severe pressure pulsations. That's why a new turbine at the Water Power Laboratory has been designed. The turbine has been designed with optimized methods to be able to operate at variable speed. Variable speed operation is not a new technology, or that kind of technology is not new. Already in the 1990s, the first implementation was done on a reversible pump turbine. A review study at NTNU that was conducted there found that variable speed operation technology for Francis turbine could give a more precise, faster, and smoother response to load variation. It could have almost 10% improvement at off design, but this was very dependent on the hydraulic design. The hill chart for this type of turbine seems to be a bit stretched towards constant guide opening, and it seems that it had a broader operation range at best efficiency point. So that's also why this new turbine had been designed. You can see this turbine on the right, and in my thesis, or my objective, is to conduct a model test of this turbine to verify numerical simulations. So the model test has to be in accordance to the IEC standard to have it accepted. The test will take place in the Water Power Laboratory at NTNU, where we have our own Francis rig that I will show you later in the presentation. In the model test, measurements regarding efficiency, pressure pulsations, axial load, runaway speed will be included. And after the test is done, the data has to be analyzed. So this is an overview of the Francis rig at the laboratory. I have marked where all the sensors is located. So you can see this is where the turbine will be installed. All the sensor except the rotational speed sensor will be calibrated, or it actually has been calibrated, because that's one of the requirements in the standard. This is an illustration of a hill chart for the reference turbine, the Francis 99 turbine. This is a way to illustrate the hydraulic efficiency for the turbine. In the y-axis you can see the discharge factor, and on the x-axis you can see the the speed factor. And the blue lines, that is the constant guide vane opening, and the red line is the variable speed curve. A hill chart seen like this will be constructed for the new turbine, and the turbines will be compared to see how this variable speed curve differs, as this curve illustrates the best efficiency for each operating points. Included in the model tests is measurements of pressure pulsations. This picture, as you can see on the presentation, is an illustration of the pressure pulsations in the Francis 99 runner, conducted by Daniel Sannes. He has been used a lot of sensors, as you can see in this axis. Oh, that was not a good drawing, but yeah, this is the sensors that he has been used, and this is the normalized frequency and the relative amplitude of the frequency. In my measurements, I will have 2 sensors in the draft tube to be able to see both the symmetric and asymmetric response. I will also have one at the inlet, and perhaps one in the vaneless space. So this is an illustration of a FFT analysis. That's one way to illustrate these pulsations. As already said, all sensors has to be calibrated. As we have, the IEC standard says that we have primary and secondary methods of calibration. Like, primary methods are the most accurate ones and don't requires calibration, as it is time, mass. Yeah, that's the most accurate. Secondary methods have to be calibrated against primary ones. In the calibration, you should find the calibration curve, you should find the calibration coefficients, and you should conduct a report of the calibration. And why do we have to calibrate the sensors? It limits the size of errors and uncertainty. To have the test accepted, the uncertainty has to lie between a certain level. After the model test is conducted, all the sensors have to be calibrated once more due to repeatability. So the conclusion for this presentation is that the model test should be and must be according to the standard. The model test is conducted to verify numerical simulations. It could be a nice way to see how a turbine designed for synchronous speed operates with as a reference, and to see how this variable speed operation differs. And after analyzes the data to see how this turbine perform experimentally, the design has to be discussed based on the results. Thank you for listening to my presentation.